All right, so today I want to talk about logistic growth. Before I discuss this topic, I would like to mention, excuse me, the exponential models. And of course, you're familiar with exponential functions, so you learned that back in pre-calculus. Using the exponential growth model, the growth of a population is proportional to its current size. So the differential equation, let's say, excuse me, dy dt equals k times y. And then the solution, the equation, would look like this, e to the power of kt. Now, if k is greater than 0, then we're talking about growth. If k is less than 0, then we're talking about the decay. It's like a little bit of review. Now, for this situation, growth is unlimited, right? However, in real populations, growth is not always unlimited, but may have an upper limit, so let's call it L, where population can no longer be sustained as time increases. This growth model is described by the logistic, we call it, differential equation. So, and it's a different model, and it looks like the following differential equation: dy dt equals k a y, and then a 1 a minus a y over that value, L, that I just mentioned a second ago. The equation that is a solution for this particular differential equation, of course, it's not going to look like that, obviously. We're done with exponential, the model. We're talking about a logistic function. So when you solve this differential equation, as your solution, you get y equals L over 1 plus, let's call it b, e to the power of negative kt. And that's the equation you get. Now, b and k, in this case, are constants. L, in this case, is a constant also, but it has a specific name, and we call it the carrying capacity. So, for example, this kind of situation where, let's say, we're talking about a population of people hearing a rumor, for instance. The maximum number of people hearing the rumor is the population itself, and so this is what we call the carrying capacity of the population. Now, the logistic model looks like this. It's not going to be perfect, I apologize. So this is your boundary. Here's your carrying capacity value. So this line is y equals to L. That's the equation that represents this boundary. And your logistic graph looks just like this. So if you noticed, as t approaches infinity, your function y approaches this particular limit, which equals to L, which we call carrying capacity. So now let me show you a few examples. So let's say, actually, I'm going to use a new page. A state game commission releases, let me just write it down, a state game commission commission releases 40 into a game. After 5 years, so T is 5. The elk population is 104. So in 5 years, that's the number we get. The commission believes that, I don't want to put that whole thing. The commission believes that the environment can support no more, so let me just put that, no more than, and this is the number of population. So that's the maximum. No more than that number. So what does it tell you? What does this number represent? Well, let's think. The growth rate of this population population P is, well, here's the differential equation. Kp, 1 minus P over 4,000. Now, we are between or equal to 40 and 4,000. So the maximum number of your population is 4,000. You probably already guessed, so that the number 4,000 is your L, is your carrying capacity. So that's your maximum number. Now, please remember, T is the number of years. Now, here's my question 1. Let's call it part A. Write a model for this population in terms of T. So it has to be a logistic model, right? Because of this fact, right? Well, if you remember, somewhere in the beginning, I gave you this formula that represents the logistic model. It's right here. Y equals, you know what, let me just copy it down here again. So Y equals, excuse me, L over 1 plus B to the E to the power of negative KT. L, we know what L is. It's our carrying capacity, and we know what that equals to. It's 4,000. So I'm just going to put the information I have, the parameters we have. So L equals 4,000, I'm sorry. Now, if you remember, I mentioned before that your B and K are constants, right? Some kind of numbers. We don't know what they are, and this is our job to find those values. L we know, so if we can find B and K, then we're all set, right? We can actually complete our equation. So far I have, well, instead of Y, they want us to use P, okay, population. P equals, L we're going to replace with 4,000 over 1 plus B e to the power of negative K times T. I'm just going to circle what I need to find. Okay. Now, if you read this problem again, they tell you what the initial condition is. Oh, right here. It says that your population is between 40 and 4,000. So the carrying capacity is 4,000, that's your maximum. But the lowest number is 40. And in the beginning it says, a state game commission releases 40, the number of the number of population. So it's 40. So when t is 0, p equals to 40. So I'm gonna put that point with the coordinates right here, and we call it initial condition. Now we need to solve this equation for b. So this is what I'm gonna do. P is 40, and I'm using this information, equals 4,000 over 1 plus, I don't know what b is, e to the power of negative k, I don't know what k is, but time is 0. So again, we're using this point. The initial condition, t is 0, p is 40. So let's see if we can solve this equation for b. 40 equals 4,000 over 1 plus e to the power of negative k times 0 is 0, so that becomes a 1. Yes, e to the power of 0 is 1, so we get 1 plus b, and 1 plus b equals, what is it, 100, and therefore b equals to 99. All right, so far we have p equals 4,000 over 1 plus, now b is 99, e to the power of negative kt. Okay, beautiful. So far we have this equation. But in order to finish it and express our final logistic model that represents this situation, we need to find k. Well, we're going to use another piece of information given. They tell you, and let me go back, that after 5 years, the population is 104. And that is why I put a point with the coordinates 5, 104. So when time is 5, the population is 104. So therefore, we get a new equation, 104, that's P, 4,000, that's your carrying capacity, 1 plus 99, we found that B, e to the power of negative k, we have no idea what that is, and we're looking for that k value, times, and what t we're going to use in this case, t value equals to 5. So now let's solve this equation for k. So we get 1 plus 99 e to the power of negative 5k equals 4,000 over 104, which is, let me use my calculator here quickly, and that is 38.462. Now 99 e to the power of negative 5k equals to, subtract 1, so you get 37.462. And therefore, e to the power of negative 5k equals 0.378. So let's put the natural logarithm on both sides. Now that's algebra 2. I don't really need to explain that. ln of e is 1. And let's see. I'm using my calculator right now. K is approximately 0.194. Okay, excellent. So now let's put it all together. So our final equation is P equals carrying capacity 4,000 over 1 plus B is 99, e to the power of negative, and k, we just found it, is 0.194 times t. And we're done. And this is our logistic model that represents this interesting situation. Now, we're not done yet. So that was only part A, believe it or not. Part B, it says graph the slope field for the differential equation and a solution that passes through the point 0, 40. Well, you know what? You can actually use your calculator to graph this slope field. I don't want you to spend time right now on that. I don't want you to do it by hand. But you do remember that, because I actually want you to sketch that model. So you remember what it looks like, right? The logistic model. We have this up boundary, which represents y equals L, and L is your carrying capacity, and in this case it is 4,000. So upper boundary is 4,000. That's your equation of that line. Now, if you remember, the initial value was 0, 40. So let's say it's here. And that's it. It's not really perfect, but something like that. Use the model to estimate the population after 15 years. Well, you're allowed to use your calculator, and now you have your equation. So all you have to do is just plug it in, right? So you need to solve for P when T equals to 15 years. So I'm going to copy my equation again. 4,000 over 1 plus 99 e to the power of negative, and that was negative for t. So P equals 4,000 over 1 plus 99 e to the power of negative 0.194, and time is 15. So all you have to do is just type this in your calculator, and you will get 626. So that's your population after 15 years. Now it says find the limit of the model as t approaches 0. Well, that's easy. So the limit as t, not 0, I'm sorry, as t approaches infinity. So remember, it's not an exponential growth, it's a logistic growth. So we're approaching this particular carrying capacity. So that means the answer is going to be 4,000, and it can't be more than that. So that's about it.